the automation and stuff. So, would you be able to tell some of the enablers? Can you tell the enablers? What are the enablers? So I'll give some clues, right? So for example, during 1912, the transfer lines, right? So one of the enablers for transfer lines to succeed that time was mass production, right? So they were able to hit the volume, very high volumes. They are able to create a huge number of parts at a very short time with a low cost. Then they were able to make high profits. So that was the one enabler, right? So I just gave some examples from the historical perspective. Can you give some examples of such enablers in the additive manufacturing? You have gone through multitude of sessions. So would you be able to tell something? You can be wrong. No, don't worry. You can type in the chat window. So I have two screens. I have one screen here where the PPT is there, and I'm seeing you here, all your names and your chat window on the second screen. So please type in. Feel free to type in some enablers that you feel are appropriate, that you felt they belong to additive manufacturing, right? So I'll ask this question in a little bit more simpler way. What do you think made additive manufacturing one of the viable technologies for the niche applications that we have currently today? Why do you think it may replace some conventional manufacturing process? If it is going to replace for some niche applications, why it is going to replace a conventional manufacturing process and how it is different? So I just want to, and also how that manufacturing scenario has changed over the years. Yeah, please. I'm giving you some time to think it over and then type it in the chat box. Or you can unmute and speak, not a problem. So anyone who wants to speak, you can please unmute and speak. I don't know whether all of you are given permission to unmute, or maybe you can raise your hand. The organizers may want to unmute you and then.
No, that's not necessary, sir. Participants can do themselves, sir.
Yeah, you can do. Okay, I think good. I got a first answer. Dr. Saranan B. So he says that advanced materials that are used in 3D printing. Great. I think the wide capability of materials. Excellent. Excellent answer. Any other? So materials capability or the complexity with which it can process very different kind of materials in one single technology. Yes. Excellent. Any other answers, please?
Sir, very complex in shape can be easily manufactured.
Yeah, so shape complexity. So it is the degree of the design freedom, right? So it is able to handle shape complexity. I'll just keep it. So I'm not having a board here to write, so I'll just keep that as a record. So shape complexity by Prithvi, right? So, or else you can type, otherwise I don't have to type it again. Shape complexity, right? So any other thing? So material complexity, I just heard. Shape complexity is one. So what about other things? Yeah, please be interactive. You can type in your answers quickly. I want some 10-5 answers. Okay, ability to get layer for a complex shape. Yeah. So you are breaking down that shape complexity into small number of two-dimensional shapes. That's a great thing. Yeah, I think that's what shape complexity is. I think I will go with the previous answer. So it's just a explanation for the previous answer, because explanation how it is able to handle shape complexity, because it's taking a three-dimensional complex object and breaking down into two-dimensional shapes, right? So that's the reason why it is able to handle complex shapes. Yeah. So I take this Dr. Saranan's examples as an explanation given to Dr. Prithvi's answer, right? So please, any other answers, please? Yeah. So any students here, research scholars, please, you can also participate. Yeah, so 2 answers I got. Any more answers? Any more answers from the participants? Okay, I'm seeing so many names, like there are 28 participants. Dr. Dharmarasa, Dr. Sudhakar Subramanian, Dr. George Victoria, Jean Robert, Jishnu, Karan Kotke, Lalit. Yeah, so I think some are they are not able to recognize, right? So you have gone through the program. So I think I don't know how many days you have attended this program. Probably from a week long, I think, right? So Dr. Sriyol, okay, Dr. Srikanth, Shivamurugan, Suresh Kumar, um, Niveta, Lalit, Karthik. Yeah, so answers. Yeah, I think I got. I'm not getting any further answers. Okay, so I am just giving you some clues. Let's see whether you are able to get the answers correctly. Now, earlier we had standard designs, right? So the designs are mostly standard. Now we are having actually a custom design, which is called, um, we are able to mass customize the designs. So the mass customization, the ability to customize the object to individual needs is what we call as mass customization, right? So the mass customization is one of the biggest enablers for 3D printing. So that's one example. So people want variety. Okay, so they don't want the same product anymore. So they want different products, isn't it? So that is one driver. So mass customization, right? So the different names of mass customizations are something like you have personalization, you have individualization, right? So these are all called another variation of the term called mass customization, right? So mass customization meaning that if I have, let's say, design which is having a huge number of variations for individual needs. I think I don't know whether I'm just cracking a joke here. So if you see, you go to Pothys tomorrow. I don't know those coming from the north. So Pothys is like a retail store for clothing and accessories. So it's a big showroom. Like in one showroom, you get everything, like saris, salwar, you know, pants, shirts, silk saris, Banaras silk saris. You get everything. Let us assume that you go to the Pothys showroom, right? And then you see everything is in one single color. So there is no variety. So all saris are same design, right? So when you go to the shop, right? So there are multiples of sections, but you go to section after section after section, you get only one design and one color sari. So how long do you think that store will survive? Right? So naturally, right? So people don't want to wear the same sari that they wore the day previous, right? So every day they want a new sari. Right? So I have seen people keeping 365 days, 365 saris and different designs. And even if some neighbor wearing something which is very similar to the color, probably they don't want it. So this is what we call about personalization. Today, cars, any product you take, so they want different colors, different designs, and then the customer is more demanding in terms of the shapes, the looks, the color, the texture, and also it is personalized, meaning that it actually fits them. Sometimes, earlier we used to kind of, we have this ready-made and custom-made dresses, right? So ready-made means like it's made for certain dimensions, and you bring it, you see whether it fits to you or not, right? So that is custom-made. You go to a tailor, he takes the measurements from you, and it is custom-made, right? So so people are moving towards the custom-made era, right? So they want products that fits them. So if they want a car where the seat fits them, they want to ride a bicycle where they can have adjustable thing, adjustable colors, and adjustable things. So they want to customize the wheel. So somebody wants to buy a car and he wants 100 things to be there in that car, right? So something like he wants to have a sporty mode, he wants to have an eco mode, he wants to have a performance mode, he wants to have a you know so all the different kinds of things, so all terrain mode. So he wants a car to do everything, right? So when you buy a mobile phone, the same thing. So you want hundreds of sensors in it and things. So products have become so complex in terms of shape, in terms of function, in terms of material, in terms of capability, right? So in terms of variety, in terms of color, texture, and things like that. So that demand, that is called what we call as mass customization, right? Or personalization. So the second driver is decentralization. I think I don't know how many of you know this for sure. China is the world factory, right? So today, if you want anything, so I take all my products here. So I have my phone made in China, I have my calculator here, which is made in China. I have a small stapler, which is made in China. I have an air conditioner, which is made in China. So it says made in China, right? So I have a mouse, keyboard, and everything. So whatever I have right now, I think this is the only 3D printed part that is made in India. But this machine is made in Europe anyway, right? So I'm seeing that there's a lot of these products that you use every day. They're all made in China. So meaning that we have centralized production to one country, and so it has become a world's manufacturing center, right? So decentralization is about producing things locally. So additive manufacturing enables it. So whereas in the mass customization, additive manufacturing is able to make varieties of parts without much trouble. Very similarly, here you are able to basically make production locally. So you can push the design from anywhere, and then you can have your own products. You can have your printer in your home, like I have seen people nowadays. They order a ebook and take printout at home. Very similar. You buy a design from design marketplace, something like Thingiverse or Shapeways, and then you have your own 3D printer at home. You print it, right? So we have seen this. So the idea here is the ability to kind of decentralize the production, decentralization, right? So type decentralization. Did anybody thought about it? Okay, I have given two: mass customization, decentralization. Can you give me some more examples, please? So I have given some idea of this. So I think I'm also giving a clue. It all ends with TAY. Some session, something like that, right? So customization, decentralization, what else? Personalization, individualization. So what other things that you can imagine? So can you give some more answers? Yeah. So any more answers? I have given enough clues. I have discussed enough. So probably I think you may get more ideas now. So because you have been listening to many speakers, so you must understand that you must have some idea about what is this, what I'm talking about, right? So okay, so let me give one more this thing. So and Srikanth is saying the PPT is not moving because I have not moved it. So I have a summary slide of all these things that I'm discussing, which I will only show because that contains all the answers to the question that I'm asking. I think Srikanth wants all the answers at once, right? So I'm trying to get the answers from you so that I can summarize them in the next slide. Okay. So would you please then tell me some answers so that I can move my slide. I want more answers. I got only two, right? So shape, material, and then I gave two. So 4 answers have come. So give me more answers. I will move my slides, please. Yeah. Okay. It's a good deal, right? So because that slide is having that answer. Any other question? Any other answers you have? So please be interactive. I know in-person programs tends to be more interactive. I can see your faces. Right now I'm seeing your photos and your first letters. Right, so I have a bunch of icons. I'll show you what I'm seeing here. This is what I'm seeing. Right, so in the screen, right. So I'm seeing all your photos and things. So yeah, please be interactive. So. Okay, so I'll give a few more answers. There is something called I think you all know about this also. There is something called distributed manufacturing, or I would say something like servitization. So have you ever heard about something called servitization? What is servitization? Servitization, I gave the answer. Now can you explain? Someone explain what is servitization? Or I will give a brand name and tell you Uberization. Have you heard about something called Uberization? What is it? Have you ever heard this term called servitizing something? I want to servitize something. Okay, so you can type. Srikanth, please type it. So I think you know typing, right? So you can type fast. Srikanth is saying, sir, I cannot interact because earphone is not working. Okay, your mic is not working or earphone is not working. If your earphone is not working, how are you then responding to me? Earphone means you are hearing it, right? So probably you are saying about your microphone, not earphone. Srikanth. Okay, so then you put it in the speaker if the earphone is not working. Anyway, so okay, thank you. So yeah, so servitization. What is servitization? I think you guys, I think you are all professors and research scholars, so you must be able to interact very well, I assume. Yes, on demand. Very good. Okay, I woke up somebody from sober, right? So great. So on demand manufacturing. So could you please explain? Somebody unmute. Can you speak? Someone, I want to hear someone. Someone speaking. What is on demand manufacturing? Okay. So someone's, I think everybody is hesitant to speak. So I think I'm forcing on them. So let's not force too much. Okay, so it is not good. So they want to stay silent, so let us stay silent. So let us not force too much. Okay, I'll tell you what is this servitization is. So servitization, okay, serve others as an appreciated compensation. Okay, I appreciate that answer, but it's an answer not for this particular context. It's an answer for another context, but not for this context. Okay, let's say you have a car. Assume that you have a car. Suddenly, someone says that I have an aggregator. You please add my car, right? So today, and then I can actually use it. Somebody can. That's what Uber did, right? So what Uber did. So people had first in the Uber model. The first Uber model is not the commercial vehicles, but personal vehicles. People had their personal vehicles, right? So when they had a free time, they can just register that in the Uber and then they can monetize it. So it's like you have a factory in your shop floor, and then you have connected those to a service discovery website, maybe a cloud-based service discovery system. So your machines are then available for someone to basically take it through cloud, and then they can use it whenever they want. So this is typically called as servitization, right? So you have a cloud-based service, and then you allow people to use it. So you have an app, right? So today you can see that there are a lot of apps that you can join and then provide service. For example, Zomato is good for food aggregation. So this is an aggregator. So manufacturing is becoming more kind of an aggregator. You have service bureaus through which you can go and register your machine to Shapeways or Thingiverse, and somebody can select you as a vendor, and then they can order parts online, then they can push that order to you. You are already in a decentralized way, and then you are very close to the customer. You can print it and deliver to it immediately, right? So you don't have to wait for the parts to arrive from China. So too much money is saved, too much the supply chain is short, and a lot of things are there, right? So these are very good examples of servitization. Great. So I gave decentralization, mass customization, servitization, personalization, individualization. Any other answers you have? Okay, let me just show the answer. So let us not go waste my time. So do you see that? So shape complexity, already told, somebody told about it. Personalization, somebody told. Decentralization, servitization, digitalization. Nobody told about this. I think it's a very simple answer. Time compression, and then functionalization. So let me tell what these things are, right? So, okay, what is digitalization? See, what is happening in the conventional manufacturing, landscape is, if you think, okay, let us just step back and think about something very crazy, right? So now we are talking about organ printing, right? So I'll just tell a small anecdote, right? So this anecdote may be very interesting for you because we have been listening about organ printing. While I was working for some government agency in United States, so I met with a guy. So his name is Craig Venter. I think those who are coming from biotechnology area, you might know him really well. So there is also a company called jcv.org. So he is the father of genome sequencing. So he was with the White House. So during the Bush administration. So he successfully sequenced the human genome. And then I happened to visit this company, which was very close to my home. So I lived in Maryland. So Maryland is home to a lot of biotechnology company. So like Medimmune and great names of all. So it's a very highly concentrated biotechnology companies who are into regenerative medicine and tissue engineering and organ transplant, organ things like that. So this guy, this Craig Winter, so what he was trying to do, you might be really wondering. So he's doing the digitalization. What is digitalization? See, for example, if you want to know, okay, so I will also introduce one more guy. So you all know Elon Musk, okay? So Elon Musk, I think you all knew about him, right? So Elon Musk is so the crazy inventor today. They are saying so his tweets can buy billions of dollars from the market suddenly, right? So he's one such crazy guy. He's very active in social media. And the day before yesterday, he was saying, "You want to quit the job, and then go for consulting," right? So he's going for things like that. So what I'm telling you, the digitalization. So I just type in there. So anyway, it's on the slide, but anyway, I just started. I kind of lost to the tribe. Digitalization. So I don't have a board to write, so I'm just writing on the chat window. So anyway, digitalization. So if you want to do an organ printing, right? So you need to know the protein patterning, right? So how do I know the protein patterning? First of all, this Elon Musk, he actually wants to go to Mars, right? So how do we send people to Mars? So you can actually put them into deep slumber, maybe in a ultra sleep mode. So we can put them in a vehicle, then we can. He's building rockets to go to Mars, right? So things like that. So the other guy I was talking about, JCB, he says he will send people to Mars, not physically but digitally. So how is that possible? So he's saying that I will do teleportation. What is teleportation? He's talking about human teleportation. So he's already working on it. He has a huge lab on it. So you give him a air, so just a strand of air, and this guy, what he can do the genome sequencing very quickly, and they send a mail to lab at Mars, so they can bring them there. Okay, so the genetic information is transferred, and he has the technology to bring the entire human there. But how do we transfer the mimetic knowledge? So we carry so much of knowledge after we're born, right? So we have seen people, we have memories, we have our high points and low points. How do we carry them with us? So that's why this Elon Musk, this guy is developing something called Neuralink. So he is already testing on animals and stuff. So you can kind of take all your memories in a chip and then transfer that also through digitally, right? And then build a human there at Mars. Looks like a really great scientific, science fiction, right? So, but it can be reality someday, right? So, yeah, so it's possible. So he's working. I have seen the room sized, the huge sized genome sequencing machine. Now he has tabletop machines, and earlier it used to take 15-20 days to get one genome sequenced. Now he's doing it in a matter of hours. So I think if you look at this kind of, this is far-reaching technological landscape that I was talking about. So the technology is something like we are, now we are looking at tissue printing and organ printing and all those aspects. People are talking about printing the entire human species or even other animal species in space, in some other planet, and then teleporting them. So why I call this as digitalization is because he converted the data. So the human data, right? So we have our own data in our DNAs and cells. He is capturing the data digitally and transferring the data digitally. Very similarly, additive manufacturing does that very efficiently. So in Industry 4.0, we call this the digital thread. So digital thread is something like you take the same digital data, use it pervasively across an entire chain, right? So the process chain, starting from your conceptual design, we call this life cycle of the product, not life cycle of a material. Life cycle of a material is different. This is life cycle of a product, which you are talking about design to disposal. A product idea comes to your mind. So I have something in my mind, and then I go to the drawing board and then give it a shape, and then assign materials and find the process to make them. And then one day I think that this idea is obsolete. Now I retired that entire product idea. So you must have seen that many cars which are running on the road, they were not on the road today, like the ambassador cars, right? So they have been on the road. So majestic, the government, so powerful they call, right? So the powerful people go on the ambassadors and contestors, but many previous. And today also we see a lot of good Honda cars, they just vanished today. And some companies also vanished. Recently Ford just exited the Indian market, but they didn't vanish from the world scene, but from the Indian scene. So what I'm saying is that the entire life cycle of the design is in digital mode. So nothing is there in the drawing, no drafting, right? So everything is digital. So you take the digital representation of 3D model, and then you fabricate them from the digital representation, and also you capture the geometry and do inspection again and all those things. Very similarly, so digitalization is a very important angle, right? So which helps you to kind of take everything in digital way. Okay, so this is what I think is from this particular paper. So you can see this from this paper. So he has given individualization and improvement of design and aesthetics, functional integration, improvement of thermodynamic behavior, reduction of component mass. So he's talking about all these aspects. So I gave it generically, but he's taking very specifically. For example, reduction in component mass means like lightweighting. So that means like he is able to take more complex shapes. Okay. So what is localization? So I talked about. So we are all talking about globalization. Suddenly we are talking something about localization. So what do you mean by localization? What is the difference between decentralization and then localization? Localization is something like, let's say, I think when you download an app, so you suddenly see that it's available in Tamil. So you get excited, you open, and then suddenly you feel bad because it's all English written in Tamil alphabets, right? So, and it's true with any other regional language. You may be coming from any part of the world. So somebody downloads them in Spanish and then sees that it's just English written in Spanish. So they get little annoyed, right? So localization means your ability to kind of understand the local needs of the customers and then customize it to the individual local people. So sometimes it's also called as localization. It means global localization. I give some examples. US always does things differently. When I went to US, so I had to do many things on my own, even filling my petrol tank and repairing my bicycle and things like that, which I'm not used to do, even making my own furniture. So I become more DIY, which is called do it yourself, or BYO, BYO, right? So it means in US, you see, they drive on one side of the road and we drive on the other side of the road. In US, they use imperial units, we use SI units, the metric units. So in US, they do things very differently in many things, right? So if I develop something for Indian market, so if I want to port it to another market, so I need to localize that, right? So that is another form of customization to regionalization, right? So I think, see, I'm getting a lot of this IOM terms, regionalization, globalization, right? So anyway, maybe I'm just infatuated with this term. So just joking, right? So yeah, so we are talking about this simplification, which is essentially what we are talking about. Is the ability to, localization is the ability to kind of customize it to the individual needs of the local. Whereas simplification is the simplified manufacturing process. It comes under the process chain. So you see here, this particular author, Vanikar, yes, Vanikar or Vanikar, I think, so I would like to go with Vanikar because it sounds more Tamil, right? So, okay, so here if you see product, so he has given multiple levels. He has given at product level, then at the process level, and then life cycle. This is what I was talking about. The life cycle, the design to dispose, not the material life cycle, which is raw material to cradle to grave. That is different. And this is company, which is like the company level things. So at enterprise level, so instead of company, I would have rather used enterprise if I wrote this paper anyway. So so the product at the first level and the process chain at the second level, life cycle at the third level, and enterprise and value chain at the 5th level. So there is one more thing called value chain, which is at the 5th level, because your enterprise doesn't stop there. You have an extended enterprise, so which is where you procure all the components. You may be an OEM, so you have a tier 1, tier 2, tier 3 suppliers, right? So I put, in fact, another one level, 5th level. So probably I think I got a lot of ideas to write a new paper as I'm giving this talk. Probably maybe I'll just go back to my students and ask them to write one more paper. Sure. Yeah, there's a lot of opportunity here. And additive manufacturing is upcoming area. So new ideas can come anytime. You can publish a lot of papers, right? So what we are talking about here is like, so we are talking about many things. So we are talking about, simplified manufacturing process. Why we are calling simplified? Okay, so I'm just giving you some, so because this program is more medical in nature, I'm just giving you some medical examples. So, so what happens is, like, when you want to go to a doctor and do some dental implants. Let's just take an example of dental implants. It's much easier to tell the story in a short way. So what they do RCT. I think you all know about RCT, root canal treatment. So before they do the RCT, they have to kind of scan your lower mandible or upper mandible, wherever they want to put the implant. And then they will make something called as a guide, surgery guide, so which actually limits your drilling depth. So whether how much drill depth you can drill the hole, and how much angle that you can drill. So both can be limited. It's a fixture, right? So it's a fixture. So you can put the fixture, and then it is a fixture for drilling holes to put the implant in. So why we cannot drill any angle or any depth? Because you have a very alveolar nerve is there, one nerve which passes through your below your bone, upper bone, the teeth and the bone, and then so if you drill into that, it is going to cause enormous pain to the patient. So you have to not to damage the nerve, right? So you have to limit your depth which you want to drill and the height you want to drill. So that part, if I want to make it for individual patients, I have to take it. So let's say you are doing it in injection molding. In injection molding, what happens is, like, you need to make a mold. The mold is going to be extremely expensive, and you have to throw away the mold once the patient goes. And if it's 1 crore mold, you have to charge him 1 crore for that particular operation, which is going to be extremely expensive. So it's prohibitively expensive. It's not extremely. So no one will buy. So there is no market opportunity for such a thing at all. So that's where the 3D printing comes in. So here, the intermediary steps are eliminated. It becomes a simplified manufacturing process. That's what we are talking about here. And on-demand, I already told. On-demand is what Solidification is. Simplified manufacturing process simplification. Improvement of mechanical flow behavior and thermodynamic behavior is functionalization. Right? Functional integration and all those things. And then complexity is the improvement of design and aesthetics. Faster product development is the time compression. So what is time compression? So people were developing earlier a lot of products, right? So when they are developing products, it makes them sense to kind of iterate it much faster. So get the product done. The trials are done much faster, right? So they need some quicker way to make a prototype. So in fact, I don't know how many of you know this. So I have been in this field for the last 20 years. So initially, it was called as a rapid prototyping. So when we were there is no term called additive manufacturing. So some layered stuff is there. They call layered manufacturing. But it was predominantly used to known as rapid prototyping, where it can actually eliminate your costly one-off-piece parts production, which you need to make in aeroforming or some other very costly process. You kind of tend to spend a lot of time in getting that one part before you commit your tooling. So you are eliminating your die, you are eliminating your tool, you are eliminating your mold, you are eliminating your fixtures, you are eliminating your jigs. So in that way, you are saving a huge cost. So you are simplifying that manufacturing process chain. So that's why it's called simplified manufacturing process chains. Right? So, okay, so decentralized production, I'll explain. So this is what. So I told that I'm just looking at enablers and objectives. What are the objectives? I think these objectives keep changing. People keep shifting the goalpost. You join a company and then they say so quality is the target. So everybody works on the quality, and suddenly quality is improved. and then they say cost is the target, then they attack the cost. Then they say time is the target, so we need to attack the time. And finally, they found out that they have screwed up the environment badly. And suddenly they are saying, now we have to focus on the environment. So we have to go to EV, electronic vehicles, right? So electric vehicles, right? So electric vehicles, and also we need to go for newer technologies which are energy efficient, which uses less amount of water, which produces less waste, right? So then they think sustainability is now the target. And once they go into the sustainability, they found other issues there, right? So that's what we are seeing here, right? So performance, time, and then maintenance cost, lead time, development, sustainability and emissions. And finally, what they do is they do the greenwashing. I don't know how many of you know about this. This is nothing but brand image. So everything they put green is only for improving their brand image. So, okay, I'm just joking. So many companies take sustainability very seriously. They work on it. But many companies, they do greenwashing. So greenwashing means they just offset their pollution somewhere, and they claim that they are very, very, they call clean production or environmentally benign production. They call all sorts of names, and they get all sorts of eco labels, right? So, but still they consume a lot of energy, which is where the energy mix is very poor. They get more energy from fossil fuel derived sources. So these are the objectives. So why additive manufacturing becomes so much famous is because it can actually improvement in all these aspects. Improvement in sustainability, improvement in emission, improvement in manufacturing capabilities, lead time, right? So improvement in the performance of the part, especially lightweighting and all those things, right? So this is one. Okay, so I think I have touched upon this topic. Now we are looking at more opportunities, right? So we have talked about enablers, we have talked about objectives. Now we are moving towards opportunities. Okay, so I'm just again coming back to the audience here. So I just want to disturb them from their regular cycles of what you call spans of attention. So we have this. Can you give me one part that you lost with 3D printed? Please type it very quickly. What is the part that you have 3D printed? If you have not 3D printed, please type I have not. Okay, so but I want answers from you. Just please type in very quickly. What is that one part that you have 3D printed in your lifetime? Maybe you could have printed thousands of parts, but the one that you printed last before coming to this workshop, or you are printing something now. Can you tell me? Or you have not printed at all, you tell me which one you found it more interesting to print, right? So you can tell anything. So just type it, whatever you can possibly. So please type in all those names of the products that you feel very excited to 3D print in future also, no problem. Please, phone stand, I think. Srikanth, okay, phone stand. I appreciate this answer. Mobile phone stand. I appreciate this answer because I have myself printed many. I'll show you. This is one which has a stand. You see, this is 3D printed. Okay, I have one more which is also 3D printed, right? So which is a pen stand, not a pen stand. Okay, I'll show one more which is also 3D printed. This is again another 3D printed stand. So this is another 3D printed. You can put a mobile here and things like that. Great. Good answer. Because everybody loves, that's the first thing that I want to do, right? So I think this is what he must have done. Lost. Okay, great. Yeah. So any other answers? Hip implant through materials in PLA. Okay. Bridge Mohan Sharma ji. Sharma ji, आपने बोला कि PLA में आपको hip implant करना चाहते हैं. ठीक है. How कुछ answers? How? What are the other answers? Sharma ji बहुत बढ़िया है. So जो आपने बोला वो PLA में कर सकते हैं. But let us see. You can print first. Start with the PLA. PLA is a very cheaper material. Smart house, great, Srikanth ji. Okay, so Srikanth wants to build a smart house. Great, good. More answers, please. Face mask, smart vehicle, pancreas. Okay, somebody wants to print the pancreas. Great. Yeah, so pancreas. So good. So organs, you can print a lot of organs. So somebody wants to print. So let me just put it here. Okay, so somebody wants to print smart vehicle. I'm not sure what you mean by smart vehicle. Srikanji, only one answer. So I think Srikant is very active. So only one answer, so that allow others. You are taking away opportunities for others. They might have thought the same answer. You must have put it there. Okay, no problem. Okay, please type. Okay, Srikanji, please type. Don't worry. Type as much answers as you want. Okay, Shivamurugan sir, are you there? Keychain, yeah, keychain is also good. So Dr. PK. So Dr. PK is I think Dr. PK, some toys. Srikanji says some toys he wants to print. Okay. Okay. So any other answers, please? Okay. So others, please. Those who have not answered, at least unmute. Somebody, I want to hear someone speaking. Please unmute and speak. Prototype devices. Okay. Prototype of a cut section of an engine. Great, sir. So teaching aid. I think Dr. P. Satyanarayana wants to print a prototype of a cut section of an engine. So he wants to print so that he can teach nicely to students. Great. So do you have? I think you have. Do you have a STL file of it? Okay. Saravana says Geneva will. That is in the Polytechnic syllabus. Good. So great. Okay. So I think these are very good ideas. Actually, these are in fact very good projects to start with. You can start printing them straight away. STL files are available. All these STL files are available, but except that smart house, somebody said. So I don't know how they want to print entire smart house. I will come to Srikant a little later. Maybe okay. Somebody wants to print MOSFET and field effect transducers. Okay, electronic 3D printing. Yes, good. So you can print antennas, you can print sensors, you can print batteries, micro batteries. You can connect them through interconnects. You can have all those things is possible. So electronic 3D printing, great. I think some electronic 3D printing is there, some bioprinting, some concrete printing. Anybody wants to print the pizza or your next tomorrow morning, everybody will be in the mutton shop in Tamil Nadu. Everybody wants to go to Sunday morning is a ritual. So everybody wants to go to the butcher shop. They buy meat in the morning. So how many of you want to print a meat? So meat printing is very famous now. So it is considered to be vegan. I don't know how far that is true. So whatever you grow the meat in the lab, So okay, smart house like a prototype model, but you can build a real house. IIT Madras has built a real house. It's possible that you can build a real smart house. I'm telling you. That's why I said I'll come back to it. I'll talk about it a little later. Yeah, you can be ambitious. Don't worry, you don't have to print a toy like a smart house. You can build your own house using 3D printing. And smart house also you can print. I'm telling you. You can have conducting circuits with electrical circuits. You can print with all the electrical connections and sensors. You can directly 3D print with the concrete. I'll tell you about that. So we are also working on a very similar project where you can 3D print an entire house. Yeah, cranial implants, great. I think somebody wants to print cranial implants. It's a very well, demonstrated case study, medically approved. FDA has done there are a lot of operations with cranial implants has been already done. Okay, so people met with an accident, so they go to trauma and then they see their skulls damaged. So take a CT scan and then get a 3D model of that space and then talk to the suppliers, get a cranial implant printed, and then bring it back to the operation theater and then put them into that place, right? So very good. Cranial implants. Surgical instruments, great. Yeah, medical surgical instruments. I think there's a lot of opportunity there. You can make a lot of surgical instruments. Yes. Okay. So how many of you want to 3D print something like an entire car? You want to 3D print an entire car? So what are the elements of car? You see you have a battery. So IC engines are gone. I'm not going to talk about pistons and connecting rods and stuff. So you have batteries, you have motors. Okay. Okay, personal protective equipment, PPE is great. So I think some wants to print personal protective equipments. In fact, I gave a talk recently how 3D printing helped people with COVID. You know that face masks. I've seen even some people printed face masks. Your personal protective equipments. We have also done a lot of work. I have lots of these personal protective equipments here. We have helped with nearby hospitals to make face masks and also exchangeable thing. When there was a lockdown, the entire supply chain was cut off. That's the reason I'm telling the localization and decentralization of production because of the context of COVID only. So we are able to supply. We supplied almost around 125 face masks to hospitals during the lockdown. And then we also tied up with nearby labs where they had all this face masks to supply. Okay. Some measuring instruments. So Ashish Shonikar, so he wants to do some measuring instruments. Great. Okay, so can you be a little bit more specific? What do you want to measure? You want to measure pressure, physical quantities, or what do you want to measure? You want to measure the X-ray, or you want to measure some the human brain activity? What do you want to measure? Measurement is a very vague term. Okay, I think I'm getting some questions from Dr. Zahir Hassan. Dr. Senthil regards, if possible, please share what is the difference between mode of organ solidification and metal solidification in terms of time. Okay, so solidification. Okay, solidification. Yes, sure, I will do that. Okay, so thanks, Dr. Zahir, for the question. Okay, I think I have got enough answers. So, in terms of opportunities, I already explained many things. Opportunities, one is material, right? So you have lots of material capability. You can mix and match materials, right? So, so you know there are bone cells. You have bone tissues. You have nerve tissues. You have blood tissues. You have so many of different kind of materials, right? So let's take an example of a bone, right? So the bone is very complex structure. I don't know how many of you have seen this. If you have seen any CT scan, in the most of the CT scan to 3D model conversion, you can also measure the bone density. So probably when you try to draw a line and then plot the bone density of from the bone center to edge, you would see that bone density, mineral density is bone mineral density is one, and the structure of the bone you see in the marrow region, right? So it's like more, I would say, a porous structure, a cancellous structure. You see that, and the surface when you reach to the edges of the bone, so they are very hard and they have good mineral densities. So you see that. So this gradation, we call this as a gradation in property, or the variation of the property to the center. You see a bamboo column, right? So you see the bamboo column, the fiber content varies. The fiber content is minimum at the center, and the fiber content is maximum at the edges. So people get, you know, that if you want to replicate a bone property, the bone cells you want to seed into there, I think you guys have listened to many lectures. You must understand the in vivo and in vitro mode of organ growing, right? So we see that, you know, we need growth factors to grow. So we see the growth factor on a polycaprolactin or a polyglycolic acid or PLG or hydro. You know, this other hydrogel and other materials, you can actually make a support structure. We call this a scaffold, and then seed some growth factors and then some cells into it, and then it grows in the lab. Or you can put that implant into the body and implant that scaffold in the body. That's where the in vivo, in vitro fabrication of cells. The cells can also come from your own body. They call autography, allography, and those things, right? So it can come from many sources. If you are taking it from your body and seeding it, and then going it outside and putting it in your body. So you see, there are different types of cells in an organ, right? So this is called material complexity. When you want to design something, you need a BioCAD, right? So how do you design something? First of all, how do you design a particular organ? So first of all, you need to understand the protein patterning, right? So most of the bioprinting that is available as on today in the market, so whatever we are seeing today, so they kind of mix materials, biomaterials, and they produce, you see, some some kind of so for example, the one that normally we use is the proteins, like the collagen protein and the hydroxyapatite. That's what the bone is made of. So normally people try to pattern it. So the protein, the collagen, the protein, the patterning them in a way can produce different kinds of organs, right? So that level of understanding, the protein patterning level of understanding, and then patterning them on a structure. So you can allow the nature to create the structure instead of you patterning them. Sometimes if you start patterning them, you will get a different kinds of behavior, right? So you are just feeding them onto a structure and then allowing the cell to grow. It's a guided growth. We call them as guided growth. We see that the lizards, they do all the time. They just throw away the tail at some point. They feel, okay, I'm just bored with my tail. I just kind of lose my tail and get something new. But we cannot do that. I want to lose my hand and just get another hand. So see, the lizard has a better brain than us. No, it's not, because it retains its growth factor. So we have lost our growth factors. So we had our growth factor till some time, and we start growing after some time. So we have to artificially give the growth factors to get that guided growth. So it cannot grow. If I amputate my hand or leg, so it cannot grow like that. So like the lizard. So the reason is because we lost the memory. We don't have that growth factors with us anymore, and it cannot grow like a hand again. Whereas lizards can grow very easily. They know the shape. They remember the shape. At any point, we have seen them grow, lose them, grow them again, lose them, grow them again. I don't know how many number of cycles, but it does it very often. I've seen. So we are not a biologist, right? So I'm an engineering scientist. So, but we have seen them grow like an entire organ together, but we have not successfully able to do it. So, but if you are able to know, I think if you preserve your stem cells, you have your growth factors, and if you can do a little bit of tweaking with the biology, I think people can grow organs, right? So they have done it. They have already proven it. So few organs have been printed. It's becoming functional after it. So I have seen some universities. I have seen the news, but I have not seen the researchers' papers that have been published that they are able to print organs, like heart and those stuff. So yeah, but we have seen them. We have done some modeling, in fact. So in 2012, we published papers. We had a voxel-based modeling system to simulate the bone growth. So the problem with what we faced is like when we did a scaffold study, the scaffold was degrading, right? So, and we started looking at the mechanical behavior of that. So we saw that there is a stimulus that is required for the bones to grow. That's why we go to gym, right? So I think many people, you see that they pay subscription fees to the gym and they build the muscles there. Very similarly, you can actually pay a subscription fee to a makerspace where they can build your organs to, right? So, but the moment you have to work out, right? So you have to apply a lot of force. It just simply, if you keep something like a scaffold and you see some cells and growth factor, it won't grow. It needs the stimulus. You have to continuously move. That's why kids play all the time and they grow, right? So that stimulus is what we studied actually in the brain, in the bone growth model. So what we did is we applied too many different types of compressive forces on the scaffold. And then we also had a software which works on something called as a voxel-based FEM, voxel-based fine tuning methods. We simulated them, the mechanical behavior. So we started looking at it from a diffusion type of problem. As the bone started to grow, the scaffold got resorbed into the body and it is excreted out, right? So what happened is, like, we tried to understand the Young's modulus gain of the bone versus the Young's modulus loss of the scaffold, and it took 100 days. So we did some studies with CCMB Hyderabad. So we found out that it took 100 days for the complete scaffold to kind of drain through the body, and also your bone starts to grow. So it's I think we found out something like 400 MPa is the strength of the bone that we have grown in the lab, but I don't know what is the real recent research, what they have done, how much faster they were able to grow the cells. So, but it normally took 3 months for the complete scaffold. Our scaffold was 50 mm by 50 mm by 50 mm, which was grown in the lab and then tested over time. So we did temporal and spatial analysis of that loss of material over time. So spatial is because you need to know where the absorption, the diffusion of this, the water and nutrients into that cells. And because that's why we make it porous, surface connected porous structures. So these surface connected porous structures helps to kind of transport the nutrients very quickly. right? So yeah, so we have been discussing mainly things about parts rates. I think I'm seeing a lot of parts now. So yeah, somebody said about solidification. See, there are many mechanisms by which 3D printing works. It's not only melting. Solidification is when you change the phase, right? So when you have a solid to liquid phase or liquid to solid phase, that only when solidification happens. But it is not the same. Sometimes it's just evaporation, sometimes it's curing, sometimes it's gelation, sometimes it's you have different kinds of mechanisms to cure. So if we look at our conventional inkjet process, we have a resin which just cures it. So high temperature curing, right? So there is some evaporation, there is some gelling, so there is some melting and solidification, and there is some mechanism like thermal curing, and there is also mechanisms like sintering. There are mechanisms like welding, joining. So, but majority of the times you see there is some phase change, right? So in a resins mostly they are in liquid state, and their polymer behave differently, metals behave differently, and then your ceramics behave differently, your metallites they behave differently, your dielectrics behave differently, your conductive ink paste, so they behave differently. A lot of conductive ink paste has been recently used, like sol gel, they just gel it. So sol gel based ink. So polycarolytic inks, the bio inks, they just evaporate, and then you get the done. You get the deposition done. So solidification, metal solidification, and the organ solidification, I don't see any comparison. See, if you look at, it's a multiphysics problem. Both are multiphysics. Solidification is a multiphysics problem. There is a flow involved. There is a heat transfer involved. Convection, convection, absorption, and then radiation, and then your phase change, heat of enthalpy, and then you have your Marangoni convection, and then flow behaviors. So all these things, if you can model them in a computer, you can understand how it solidifies. Very similarly, the organ model, we have also done some models how cell grows, the kinetics of cell growth. That we need. So the kinetics of the material growth, the grain boundary growth, is completely different than the cell growth kinetics. So the kinetics of cell growth we have also studied sometimes. So we have seen how the cell actually, the rate at which the cells grow and the rate at which this grains grow, they are no way comparable in the temporal scale, right? So solidification happens in a fraction of time, whereas this growth happens over 100 days, 200 days. So they can never be comparable. So I think Dr. Zahir, I tried to compare and gave some with whatever knowledge I have given, right? So some knowledge about whatever I had, whatever I studied. Probably you can read more about it, so you will understand more about how to compare and contrast between two different kinds of world. So you are trying to basically compare the robotics to real human being, right? So you can print a complete robot or print a complete human. So are they two different things, or are they one? So the solidification in the metal can much faster, but the growth doesn't happen that much faster. Okay. So somebody said some prototype of section of engines. So I think that's a patient specific devices, casting parts, Ashish Shanikar, automotive parts. Can we use protein-based PLA? Okay, so PLA is like biocompatible material. But PLA is not the solution for all problems. So PLA is good. It's biocompatible, biodegradable. So it's cheaper. It can be used with any type of printer, whether it's a consumer printer or a desktop printer or a commercial printer. So you can use it with them. So not a problem. But it has got its own problem. It has got quick aging property. It becomes stiff, so it becomes brittle. So yeah, you can mix and match anything. People mix wood biomaterials with them, but I don't think PLA can be used for proteins and all. So you can use micro dispensing techniques, not the deposition extrusion techniques. You can use micro dispensing and then mix the proteins with agents. So you have a lot of we call this additives, right? So you can add a lot of additives, reinforcements, and things like that. So you can mix. So for example, so the materials that your bioprinter normally employs. So you can see them. They can use different kinds of protein. For example, normally what people do in the lab scale is they use bovine serum mostly to carry this and do some studies on them. So you have to maintain the pH level. You can use any reinforcement, but you have to appropriately maintain the pH level, and then use it in a contamination-free environment, and things like that. So PLA is not a solution. I think PLA is mostly used as this thing. So you can use it as a scaffold. People have tried it. Polycopyrrolate, they have tried cellulose acetate and things like this. But it's still under it's still under study. So they have done a lot of papers have been published, but still nothing is commercialized yet. So on PLA, so people have studied it. So it's cheaply available. Everybody wants to try it. They have tried it, but I think it's not commercialized yet. So we have to see the FDA approvals and things like that. So okay, so Bridge Mohan Sharma ji. So which new novel material could be used for dental implant? Which material is used by the dentist nowadays? Okay, so there are different types of implants, in dentistry, right? So I want you to be specifically suggesting what. So any dental titanium screws they use, and then they put ceramic thing, and they also use if you want to 3D print normally the cobalt chrome moly they call, right? So COCR. So the cobalt chrome moly alloys are the most widely used medical grade implant materials as of now. You can use titanium, not a problem. If you are little, I would say, wealthy enough, you can also print in gold. I'm not joking. So gold 3D printing machines are available, so you can print in gold. So I have seen people who have implants in gold just to show off their wealth. But it's a good material. It's a biocompatible material. So when you chew it, a little bit of gold goes to your body. It's okay. So it's not proven, scientifically proven, but people still eat that. They call a small piece of gold. So they call Tangapaspam in Tamil. So I don't know what they call it there. So they eat gold, right? So you can make it in gold. You can make it in cobalt chromium. You can make it in titanium. Steel is for people who can't afford any of this. So ceramics also people use, but it's a cup they put on top of the screw. So steel is also has corrosion resistant properties, but you have to do some revision surgeries after some time. They found titanium to have some issues. Titanium has a stress shielding issue. The issue is like the stress shielding issue is something like I already explained. The bone needs stimulus to grow, right? Whatever forces that give, like the bones degrade constantly. Every year you are replacing your bone cells because they degrade constantly, and then new birth cells form. So you have to, as you bite more, and then new cells grow, right? So when you put a titanium, the stress that the bone receives is shielded by the titanium implant. So now they have gone into magnesium. So that's a new material that people are trying to explore. So to avoid that stress shielding effect, they are going for magnesium implants, but it is extremely difficult to process them. They are highly reactive materials, just like titanium. So it's very difficult to process magnesium implant. But recently, I've seen a lot of new research papers coming up with magnesium implants just to avoid the stress shielding effect. So magnesium kind of allows people to avoid the stress shielding effect. So that is the main problem with the titanium implants that recently people found. So yeah, so I think you can use all these materials, not a problem. Okay, so let us just go back to the slide. I think so I need to also take the organizer's permission to continue. I don't know how long they have planned me to keep me here, so otherwise they will kick me out. So organizers, please let me know when I need to stop. I will stop it at this point. And also I heard that there is going to be some valedictory program where some chief guest is going to join. So let me just go to the slide very quickly. So this is what I was trying to explain. So the customization angle and the complexity angle and the volume angle. So we are going towards a more complete manufacturing freedom. So this is what I'm trying to explain. So 3D printing. So you can consolidate many parts. So this is one design opportunity. So you can functionalize the parts, and then you can add multiple functions into one part. So this is the example I was trying to explain about the drilling. When you're drilling holes, you need a surgical guide like this. So this is now these are not made in India. So now there's a company called Noble Biocare. They make all these kinds of surgical tools and things like that. So this is a fixture, like we normally call this in manufacturing work as a fixture. It limits the distance to which you have to drill and the direction angle to which you have to drill. And you have a software called surgical guide software. You take a CT scan, and then CT scan, your mandible is put out flat, and then you can select an angle you want to drill in the software, and then you get this design automatically from the planning software. So surgical planning software. So this is hearing aid shields, which is custom designed. And also you can make forms like the bone structure I was talking about. So you can reverse engineer a bone structure, and then you can create a reference volume element and do Boolean around that. And then this is a titanium foam which you see here. So you can create such a very complex structures for bones and others where you want nutrients to pass through, right? So this is again topology optimization where you can get very complex shapes. This is for prosthetics and stuff you can do, right? So you can actually have lattice structures inbuilt, structures which is very porous to outside surface. You can do generative design where you can get more design outcomes. Is another opportunity, right? So generative design is another opportunity. This is a heterogeneous objects I was talking about, the bone structure, where you have metal plus ceramics where they are graded into one thing, right? So you can see that the structure is going from one end to the other end. It is graded very nicely. This is the work from IIC Bangalore. So you can see that you can actually vary the material property to which get different kinds of materials. You can assign a function to individual lines, and then the material property can be varied along that line. So hierarchical complexity, by nature, you see most of our body looks more hierarchical in nature. You look at it from your macro level to meso level to micro level to nano level. The structure remains the same. You can mimic that. So you can biomimic that, and then create such a complex cellular structures, right? So these things can be used as scaffolds. These things can be used as growing organs, and so these structures are extremely good. So you can actually take a structure and repeat that in multiple scales. You take a molecular structure and then repeat them, pattern them. You get up to the nano level. So you start from the nanometer, 200 nanometers, and then 10 centimeter up to level. You can just pattern them in the structure. So this is a hierarchical complexity. You can model them very easily. You can build extremely complex hierarchical structures which could be mimicking your actual bone and properties and things like that. This is like exactly how structure can be modeled. So you can also, this is another example of complex material, colors and structures which you can actually fabricate. You can vary material properties also from one end to other end. You can see 100% copper here, 100% nickel here, and they have gradually changed over different dimensions. So this is a material complexity. You have this opportunity here again. Functional complexity is about flow and other behaviors which can be improved, right? So you can put electrical properties, optical properties, thermal properties, flow properties, and conductive, all those things into one. So you can also integrate electronic components as part of mechanical component, which is the functional integration. So this is the one slide that I want to basically tell about. Like you have all this form complexity, hierarchical complexity, material complexity. They get you, like reduction in design space, flow dynamics improvements, energy consumption. This is the objective enabler that we discussed in the first slide, right? So this is the objective. What you see here is this one is the objective, and this one is the enabler. So we are getting that here, right? So finally we are talking about AI in 3D printing. So with this thought, I think, so organizers, how much time do we have? So I think, are they here? Sankar Narayanamurthy sir, are you there? Hello.
Yes, sir.
Sir, how much time do we have left?
Sir, if you have finished means we can get on to validatory, sir.
Oh, that's great, sir. I think, so give me 5 minutes, sir. Just wind up.
Okay, sir. Okay, sir.
Okay, great to hear. Okay, so so we are talking about printing organs and printing biological substances. We want to understand one thing very clear. So we are trying to basically mimic a lot of natural functions. One of the things that we want to do is complete automation. It's the artificial intelligence and 3D printing. So we want to take the design to be completely automated. So whatever design that we do. So artificial intelligence is about the ability to diagnose diseases, ability to diagnose diseases and do image processing. I think you know that right now you can scan a simple retina scan. With retina scan, you can diagnose so many different things. So you have very handheld devices. Doctors are provided with excellent diagnostic tools which uses artificial intelligence and machine learning algorithms to learn from the data, and then help the doctors. You cannot replace the doctor, but help the doctor to kind of make an informed decisions about diseases and about things like that. So very similarly, You can also use artificial intelligence in coming up with very novel shapes and 3D printing. Okay, so I'll stop at this point. I'll leave the uh, podium to the organizers for. Thank you. Okay. Yeah. So, any questions? If there are no questions, we shall go to the sermon directly from here. Yeah. So I think I have a question. Hydrophonic coatings for polymeric parts, polymer materials like PLA, ABS, TPU, PVA heaps. Okay. So so this hydrophobic property, right? So we want to basically, I think, if you want to basically see that whether can we give some coatings on this particular materials. So especially polymer materials, right? So I think ABS is okay, and I don't know much about PV. So, but PLA, ABS, TPU, we can give hydrophobic coatings, not a problem. So it can help you to kind of make some improved functionality over the surfaces. It's possible. Yeah, it's done. It can be done, not a problem. But yeah, PVA, I'm not sure, but yeah, you can do it on TPU, PLA, and ABS. It's possible. You can give a hydrophobic coating, which can help you to have an improved functionality. This is what is functional integration. You can take any functional aspects of it. So, for example, you want flame retardance, you want something like electromagnetic shielding, interferences shielding. So you can add any function you want. You can add acoustic functions also, things like that. Okay, there was a question whether computer science students can also use 3D technology. So they are the one who are using the 3D day and night. Okay, so most of the computer graphics were developed by computer science students only. All the three-dimensional solid modeling that we enjoy was developed by them. And 3D printing, in fact, many algorithms are written by them. So computer science is still all the games that you play, right? So the PUBG and all the other games in computers, the Xbox and Sony, they are the results of the ASEAN SIGGRAPH conference. It's from Stanford and Carnegie Mellon and Pittsburgh and Penn State. So these algorithms came from there. So, and they also develop a lot of 3D technologies today. So have haptic technologies, and so the 3D modeling community largely benefits from computer science. In fact, I remember one computer science faculty. I'll show you. His name is George Hart. So 20 years ago, he used to have a website. So he was from Stony Brook University. I'll show his interesting collections first. Stop here. Maybe you might have heard about this professor. His name is George Hart. So he makes very interesting sculptures. He was a professor at computer science department. I'll show his cool projects that he has done with 3D printing. So he develops a lot of mathematical surfaces which can be converted. So we used to print when we were students in 2001, 2002. We used to take his STL file download and we used to print them in our lab and stuff. So I'll show you some of this. Maybe you can just the Museum of Mathematics. Okay, so he has created a lot of things. So maybe I'll just show some. So this is one sculpture he has developed. There are so many different sculptures he has developed. So I just want to show you here. So this is these are some constructions. So he shows a lot of this 3D printed objects also. Computer science sculptures. Yeah. So it's a course, I think. Yeah. So there's a lot of. You can see here some of his rapid prototyping models. So these models are the one that we used to take from him in 3D print. So he's a computer science student. He does a lot of very interesting 3D models. You can just see these are the models that he printed. So he develops a lot of these mathematical surfaces. So these are not modeled; they are actually generated. This is the power of generated design. So you can see 3D printing mathematical models. So what are the mathematical models he has developed? So with all the softwares that he has, these are the equations. These are the parametric equations with which he actually developed these models. So they are all organic. They look very bio, right? So I think you must be able to see these things. So you used to appreciate this. He has a lot of sculptures in the US. So if you go to US universities, they have a lot of these sculptures. Every university will have one sculpture which George Hart has made. So the student, you can actually in your college, maybe in the Kamarajar College, you might want to take some of his sculptures and put it everywhere. So in the labs, like if you have a maker space or innovation lab, so you might want to take some of his sculptures and try to build them on. We have built 2-3 sculptures of his, very interesting sculptures. You can see he has built them in multiple places, in schools and colleges. So very interesting sculptures. He's a computer science guy, but he's very much interested in geometry and 3D structures. He developed them by programming, not by modeling. So that's the beauty of it. So, okay, so thank you. I think I'm exceeding my time. So Srikanth ji, okay. I think I gave the answer to Srikanth also.